Okay, next we have electric potential of continuous charge distribution. We know that if we bring a charge from, let's say, from this point A to point B, such that this point A is at infinity and this point B is at a distance r from some origin O, and we are bringing a charge, let's suppose this is the charge Q, from this infinite distance to this point B, then we have the electric potential of this point charge is given by this relation. V is equal to 1 over 4 pi epsilon naught K over R. This is for a single charge. Like we are bringing this single point charge Q from infinity to a point B, which is at a distance r from this origin. Then the potential of this charge, or the potential stored in this charge, is given by this relation. In the same way, let's suppose we are bringing many charges, endpoint charges, to a single point. Let's suppose we have many charges. These are many charges, and we are bringing all these charges to, let's suppose, this region. Then we know that the potential of this collection of charges, the potential of a collection of point charges is V is equal to 1 over 4 pi epsilon naught, and we have the summation. I started from 1 up to n. Let's suppose we are bringing n charges to this region, then its potential is given by this relation Qi over Ri. Let's say this is equation number 1 and this is equation number 2. Now here the charges are countable. Like we have n charges, like 1000, 2000, 500 or 200 200 charges are there. But if the numbers is uncountable, like we have a continuous charge distribution, then for continuous charge distribution, we replace the summation by an integral. So for continuous charge distribution, we will replace this summation by an integral. So we have the potential of continuous charge distribution is given by 1 over 4 pi epsilon naught into integral of dq over r. This is for continuous charge distribution. Now, the continuous charge distribution is either line of charge with linear charge density. If the continuous charge distribution are on a line of charge, like for linear charge distribution, with linear charge density, lambda given by lambda is equal to dq over dl, or this is lambda, dq is equal to lambda dl. So for linear charge distribution, the potential will be V is equal to 1 over 4 pi epsilon naught integral of lambda dq over r. This is for linear charge distribution. Now if the charges are distributed over a surface, for surface charge distribution, with surface charge density sigma, which is equal to charge per unit area dA. Now from this we get the charge dq, which is equal to surface charge density times area dA. So the potential for surface charge density will be, we replace this dq here in this equation, we replace this dq here in this equation by this sigma dA. Like we have, this is the relation for the potential of arbitrary charge distribution. So for the surface charge distribution, this relation will be replaced by V is equal to 1 over 4 pi epsilon naught integral of, instead of dq, we will replace it by this relation sigma dA over r. This is for surface charge density or surface charge distribution. Similarly, if the charges are inside a volume with volume density rho for volume charge distribution, with volume density rho, which is equal to dq over dv. From this we get dq is equal to rho into dv. So replacing dq by this rho dv, we get the potential of volume charge density. V is equal to 1 over 4 pi epsilon naught integral of rho dv over r. This is for volume charge distribution. Volume charge distribution. So this was all about what we call it, the electric potential of continuous charge distribution. Now we will apply this relation by considering some specific problems, and the first problem is potential due to ring of charges. Potential, first one is potential due to ring of charge. We consider a ring. Let's suppose this is a ring. And the radius of this ring is, let's suppose the radius is r, capital R. And we have charges, total charge q on this ring. Now we have to calculate the potential at point P. Let's suppose this is the point P, which is along z-axis. This is our z-axis. This is the point P. So we take a small length element. I take a small length element. This is the length element. With length, I call it ds. You can call it dl also. And this length element contains charge dq. Now this point or this length element looks like a point charge, and it is, I suppose that it is at a distance r, small r, from this point P. Now the potential at point P due to this charge element with charge dq and length ds is given by, we already did it before, V is equal to 1 over 4 pi epsilon naught, it's dV because the potential due to this one is dV, 1 over 4 pi epsilon naught dq over r, because the distance from this length element to this point P is r. Now the charges are on this ring, so it is a linear charge density. The linear charge density is lambda is equal to dq over ds, charge per unit length. So charge is dq and length is ds. From this we get dq is equal to lambda ds. Let's say this is equation 1 and this is equation number 2. So using equation 1 and 2, two and 1, we have dV is equal to 1 over 4 pi epsilon naught lambda ds over r. The potential due to whole ring of charge q is, we will integrate this potential. So on this side we have V, which is integral of dV, which is equal to 1 over 4 pi epsilon naught integral of lambda ds over r. Now I can write it as also, we have V, which is equal to 1 over 4 pi epsilon naught, 1 over r is also constant, so I will keep it outside of the integral, and we have integral of lambda ds. As we know that dq is equal to lambda ds, if I integrate both sides, I have this relation. This will give us the total charge q, this one, this side, and this is equal to integral of lambda ds. So we can write it here, the lambda ds is the total charge on the ring. So if I put this one, lambda ds is equal to q, and above this relation we have the potential, which is equal to, in this relation, which is equal to 1 over 4 pi epsilon naught 1 over r into q. V is equal to 1 over 4 pi epsilon naught q over r. Now if you look at this figure, then we have, this is the radius, this is r, and let's suppose this is my theta. Then applying Pythagoras theorem to this triangle, let's say this is, I call it P, this is my origin, and this is, I call it, let's say, point B, yes, capital B. So from triangle, from right angle triangle, because this angle is 90, from right angle triangle, and the triangle is OPB, we have r square is equal to, this is hypotenuse, so r square, hypotenuse square is equal to base square. Base is from this point to this point, this distance is z, because this is along z axis. So z square plus this distance, which is the radius of the ring, r square. R is equal to z square plus r square square root. So if I put this value here in this relation, we have the potential, total potential of the ring due to ring of charge is 1 over 4 pi epsilon naught q over z square plus r square whole 1 over 2. Now this is the potential at point P. At point P due to ring of charge. This is the potential at point P, which is at a distance z from the center of this ring. So this is one practical application for the continuous charge distribution. In the next video I will do the potential due to disk of charges.